Garden of the Salish Sea Curriculum is the Whatcom County affiliate of the nonprofit Pacific Shellfish Institute, based in Olympia. We have worked to support students and teachers since 2012 with a shellfish-based K-12 curriculum aligned with the next generation science standards.
Today we are here at Drayton Harbor. We're actually at the Blaine Harbor Marina, and we're going to test water quality. Some of the water quality tests we're going to be doing are pH, dissolved oxygen content, and salinity or salt content. And we're also going to look at some fecal coliform or fecal bacteria data.
Let's take a moment to recognize where we are. The Coast Salish have a saying, when the tide is out, the table is set. The Coast Salish have been stewards of the Salish Sea and their traditional and customary fishing grounds for thousands of years. They continue to rely on these resources today. Both Birch Bay State Park and Drayton Harbor are important Whatcom County shellfish protection districts with recreational and commercial shellfish resources. Here are some tips for how you can be a good steward while exploring the intertidal zone. For more details on these tips, visit our Family Beach Exploration Guide. What is in the water that comes out of your tap? Is it just H2O, hydrogen and oxygen atoms? Water quality is most commonly viewed from the perspective of what you are using it for. Water full of dirt might be okay for watering your garden, but you would not want to drink it. There are physical, chemical, and biological characteristics that make up water quality, and they're not always visible. The acidity of the water can be tested using pH tests. The pH scale ranges from 0 to 14, with 7 being neutral. Most organisms exist in the neutral pH range, which is 6.5 to 8.5. Human blood is 7.4, and seawater is typically 8.2. The salinity and minerals in the seawater contribute to a higher pH. These minerals, like calcium carbonate, are important for shellfish and other calcifiers to form their shells and survive to adulthood.
All right, one of the ways that we can test for pH is with litmus paper strips. So we have these little strips here. We can dip them into our water, hold for a second, and then that will change color, and we can compare the color change to this paper.
It looks like our litmus paper test is showing us that the pH is around 8. We can also test for pH using a color indicator that we have here.
We put 5 milliliters in each of these vials, and we're going to put them into this tube. And then on the left-hand side, we're going to add 6 drops of our color indicator. 1, 2, 3, 4, 5, 6. And I'm going to put a cap on it. And take it out and actually invert it a few times. So that we mix all that color in there. And then we can get a close-up of the color difference here.
We're going to spin this wheel until we find the color that matches the closest. It looks like 8 is the closest match. This is the same as what our litmus paper tests showed as well.
Today we are going to be looking at dissolved oxygen and how much of it is available in the water column. Just like you and I need oxygen in order to survive, salmon and marine organisms need oxygen to breathe too. Think about the other animals we've seen in this virtual field trip. Both the kelp crab and oyster need dissolved oxygen in the water to breathe. Water temperature is also critical for available oxygen, because cold water holds more oxygen in it than warm water. To test for dissolved oxygen in this water sample at Drayton Harbor, we need to perform a series of chemical tests. Our first step is to fill our sample vial to the top with water and add chemical 1. We need to invert the sample 10 times after each chemical is added. Take a good look before and after we add chemical 1 to the water. Chemical 1 sterilizes our water sample, making it appear more clean and clear. Bacteria and other microbes in our water sample also need oxygen to breathe, but we cannot take an accurate reading of how much oxygen is in our sample if these organisms are presently consuming it and altering the available amount. Chemical 2 will bind to any available oxygen molecules within our sample and result in a chemical reaction indicated by a color change. Pay close attention to how the water solution changes and the reaction that will occur as we add chemical 2 and invert it 10 times. Notice how the color changed and our solution of water now looks like a solution of orange juice. That is because the chemical has begun binding to all the oxygen in the sample. We need to let our sample sit to ensure that all molecules are binding. This process takes about 5 minutes, so we have fast-forwarded the video. Once the particles called flocculant begin to settle to just over half the volume of the sample, we know we are ready for the next step. Now we are ready to add our next chemical. This chemical will also result in a chemical reaction for oxygen binding. Notice how the chunkiness of our sample has gone from an orange juice-like texture to a sparkly similarity of apple juice. Okay, so to measure dissolved oxygen, we want to know how much oxygen per parts per million is in the water sample. And salmon and other fish need about 6 parts per million oxygen in order to survive. So just like at home, you would use a measuring cup to bake bread or cookies with your parents. This is a fancy scientific measuring cup that holds exactly 1 million molecules. So I'm going to pour some of my sample into my measuring cup so I can test for how many pieces of oxygen or parts per million are in the sample. Okay, so I have my vial that has 1 million molecules in it. I'm going to pour it into another vial so I can do my titration. To do this test, we need to perform another chemical reaction called a titration, using a chemical solution called sodium thiosulfate. Our goal is to see how many drops, or how many parts per million indicated by each drop, it takes for our solution to go from yellow back to clear. Let's count and see how many drops it took, and thus how many parts per million oxygen is in the water sample here at Drayton Harbor. 1, 2, 3, 4, 5, nothing yet, 6, 7, well, it's starting to change, 8, a little more, 9, oh, maybe one more, 10, let's do one more just for safe measure, 11. And we have our chemical reaction that occurred from the yellow color that we started with to crystal clear. So it took 11 drops, or 11 parts per million, to tell us how much oxygen was in that 1 million molecule sample. So we have 11 parts per million oxygen in the water here at the Blaine Marina. Less than 6 parts per million is a sign of poor water quality. 6 to 9 parts per million indicates fair water quality, and the minimum that fish like salmon need for survival. And 9 to 15 parts per million indicates excellence.
Next, we're going to look at salinity. Do you think that Drayton Harbor is saltwater or freshwater? What about California or Dakota Creek? Drayton Harbor is marine or saltwater, and there are many freshwater creeks like California and Dakota that flow into Drayton Harbor.
One of the ways that we can test for salinity or salt content is with a hydrometer. What this does is it tests the density of the water. So if there's more salt in the water is more dense, and this little arm will start to float higher because of the density, and it floats on that more dense salt water.
This hydrometer measures the salinity in parts per 1,000, meaning for every 1,000 water molecules, there's 1 salt ion. The salinity of fresh water is near 0. Since saltwater has a higher density than freshwater, when a stream flows into saltwater, the freshwater will tend to float until it becomes mixed in. This test is showing that we have about 25 parts per 1,000 of salt in the water. This is lower than normal, which may be due to the heavy rains that we've had over this last week. This freshwater is likely floating at the surface, causing us to have a lower than normal reading. Fecal bacteria get into streams and estuaries from the poop of warm-blooded animals like pets and livestock when it rains or from sewage leaks. Fecal bacteria indicate there may be bacteria in the water that can make us sick. The samples are taken back to the lab where they're able to be filtered. A single bacteria cell divides and grows into a visible clump or colony, as shown here on this plate. A shellfish growing area is approved for commercial harvest by the Washington State Department of Health when the average fecal coliform bacteria count is less than 14 colonies filtered from 100 milliliters of marine water, and the average is less than 43 colonies per 100 milliliters. Washington State Department of Health and Whatcom County regularly test Drayton Harbor for fecal bacteria to help keep us safe. The most recent data for Drayton Harbor showed that the harbor meets the safety standards for eating shellfish. Visit our website at gardensalishsea.org for more virtual beach walks, family activities throughout the summer and fall, and sign up for our newsletter. You can also take the Salish Sea Challenge, which has ideas for keeping our watershed healthy.